In this video, we will talk about some consequences of the Cauchy Formula Extension, as well as the Liouville Theorem, and also a quick mention of the Fundamental Theorem of Algebra, which is an application of the Liouville Theorem. This is our overview slide, which we'll spend less than 5 minutes on before going over each topic in more detail and more examples. I do want to mention, because many of these theorems, while they are important and they're interesting to do, they are not necessary for us to continue with the next chapters of our course. So often I might skip this chapter or these topics if I were pressed for time. But I do like this topic in particular because it gives us a proof of the fundamental theorem of algebra, in which case it gives me an excuse to show you some of the fundamental theorems of mathematics, which is on my next slide. So before we go into our topics of the Cauchy Formula Extension and Liouville's theorem, I do want to point out some of the fundamental theorems of mathematics. There are many fundamental theorems, but these are the ones that you've probably seen before, and you should just be aware that they're the fundamental theorem. So the first one is the fundamental theorem of arithmetic, and that's the factorization theorem. And you know this one, that every integer greater than 1 can be represented uniquely as a product of primes, and uniquely up to the order of the factors. So you've been doing this since 4th grade whenever you have a number and you have to factor it. The next is the fundamental theorem of algebra, which we are going to be proving using Liouville's theorem. And this is that a polynomial, given a polynomial, that the polynomial will have at least one zero. You do this all the time in algebra, you're looking for the roots. Okay. The fundamental theorem of calculus, this one is the one that links the concept of differentiation with the concept of integration. And we have here, so if we take the integral from a to b of f prime of x dx, that will be f of b minus f of a. In other words, the antiderivative is evaluated at our endpoints. And you use this all the time in calculus. And last, if you've had linear algebra, there's the fundamental theorem of linear algebra, which was the rank theorem that said the dimension of the column space and the null space of an M by N matrix A satisfies the equation the rank of A plus the null of A equals the number of columns in A. And now before we overview what we will cover in this video, I want to do a quick review of our Cauchy integral formula, which is let f be an analytic everywhere inside and on a simple closed contour C taken in the positive orientation. Our Cauchy formula then said f of z, where z again is a number inside the circle, equals 1 over 2 pi I integral from C f of s ds s minus z. Z is interior to C, and s are points on C. And the remarkable thing about this, if you remember, is that means that our function at the point z, where z is interior to C, is totally determined by what happens on the curve, the boundary of the curve, because we're taking this line integral, and then we divide by s minus z. The extension told us that f prime of z, so the extension applies to derivatives, f prime of z is equal to 1 over 2 pi I line integral over c f of s minus z squared, and in general for the nth derivative, fn of z is equal to n factorial over 2 pi I line integral over c of f of s ds s minus z n plus 1. Our new consequences or theorems that we get from this Cauchy extension is if a function f is analytic at a given point, then its derivatives of all orders are also analytic at that point. The next theorem, let f be continuous on a domain D, then if the line integral around C, any closed contour in D, is equal to 0, then we can conclude that f is analytic throughout D. We kind of had the converse of this theorem in a previous video when we talked about the Cauchy-Gorsatz theorem. And then here, the last theorem, the Cauchy estimate, also the Cauchy inequality. Suppose that a function f is analytic inside and on a positively oriented circle CR, that's the circle with radius r, centered at z0 with radius r, if m sub r denotes the maximum value of the modulus of f of z on CR, then the modulus of fn of z naught is less than or equal to n factorial, that maximum value, capital M sub r, divided by r, the radius, raised to the n. So then it's an inequality, or you can consider this an estimate because it gives you an upper bound on an estimate. And then this last theorem, Cauchy's estimate or Cauchy's inequality, will help us to prove Liouville's theorem that says if a function is entire and bounded in the complex plane, then f is constant throughout the plane. And this to me is a little surprising because it's saying if f is merely analytic throughout the entire complex plane, but it's bounded. In other words, it has a maximum value. It doesn't get arbitrarily large, so it's bounded, then automatically f is constant. I find that a little bit surprising. But as an example of this theorem, we're going to use this theorem to prove the fundamental theorem of algebra, which says if you have a polynomial, p of z is equal to a naught plus a1z plus a2z squared up to a n z n, then it has at least one zero. And that's our overview of this video. The rest of the video is mostly going through the proofs of these 4 theorems. Now, and actually this example is also a proof. So 5 proofs, which often I don't do a lot of in this class, but here we are. We're going to be doing some proofs and nothing but proofs. If you want to just take note of the theorems and skip the proofs, in my class, I would think that is just fine. The first theorem we will prove is that if a function f is analytic at any given point, then its derivatives of all orders are also analytic at that point. And if you think about it, this is quite remarkable that you can say all the derivatives will be analytic as well. We are going to start our proof with what we're given. F is analytic at any given point. So we're going to say f is analytic at a point z naught, where z naught is an arbitrary point. By our definition of what it means to be analytic, this is from chapter 2 on our video of analytic functions. A function f of a complex variable z is analytic at a point z naught if it has a derivative at each point in some neighborhood of z naught. So when we say f is analytic at a point z naught, that means there's a neighborhood, z minus z naught less than epsilon, so kind of a circle of radius epsilon of z naught throughout which f is analytic and has a derivative. And I have this picture to remind you what this neighborhood looks like. It's all the points z such that the distance from z to z naught, that's the center of our neighborhood, is less than epsilon. So it's essentially the interior of the circle where the radius, I should draw the radius, is equal to epsilon. So we're saying that for f to be analytic, that means there's this neighborhood around z, this yellow shaded portion, where f is analytic and has a derivative. Now that we have this neighborhood in yellow, we can draw a positively oriented circle c naught centered at z naught with the radius epsilon divided by 2. Essentially what we want is a circle that's entirely contained inside the analytic portion. So we just chose a radius of epsilon divided by 2 just to make things easy. So if this is epsilon, this is our circle here, c naught, and then f will be analytic inside and on c naught. And now for our reference, I have the review of our extension of the Cauchy integral formulas over here. And we will use this one using n is equal to 2. In other words, the second derivative then is equal to n factorial, which is 2 factorial, 2 pi I, integral over c, f of z dz, z minus z naught to the n plus 1, so that would be to the third. And just note over here, I replaced our variable here in this integral is s, but over here our variable is z. So I replaced s everywhere in this formula with z. And then here, the idea is that this z in the formula is the center of our circle. So I just replaced that with z naught, which is the center of our circle here. Part of this extension of the Cauchy integral formula is that once we have this formula for the nth derivative of f, that means that this derivative exists. So for our problem here, what we just showed is f double prime exists throughout the neighborhood that we're considering, which means if we look at the definition of what it is to be analytic, it means that there's a neighborhood throughout which f is analytic and has a derivative. So in this case, we can conclude that f prime is analytic because it does have derivatives that exist in this neighborhood, and the derivative is f double prime. So what we have shown is that f prime is analytic. And then we can apply the same argument to the analytic function on f prime now. So instead of f, we're going to use f prime to conclude that its derivative, f double prime, is analytic. And we can keep continuing to do this to show that all orders of the derivatives are analytic. Hence, we've proven our first theorem. If a function f is analytic at a given point, then its derivatives of all orders are analytic at the point. We have a corollary that I will state without proof. If we write a function f of xy as u of xy plus I v of xy, we separate out the real and imaginary portions. If f of xy is analytic at a point z, then the component functions u and v have continuous partial derivatives of all orders at that point. The next theorem we want to prove is to let f be continuous on a domain D. Then if the line integral or the closed curve integral C, f of z dz equals 0 for every closed contour C in D, then f is analytic throughout D. And if this theorem sounds a little bit familiar to you, that's because this theorem is the converse of the Cauchy-Gorsatz's theorem for simply connected domains. And I have the Cauchy-Gorsatz's theorem and the Cauchy-Gorsatz's theorem for simply connected domains here for your reference. So Cauchy-Gorsatz's says if a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. And for simply connected domains, if the function f is analytic throughout a simply connected domain D, then for every closed contour lying in D, then the closed contour integral is equal to 0. And so this theorem here, because it doesn't talk about being analytic at all points interior to and on the simple closed contour, we have to go and use or compare it to the simply connected domains theorem. So if f is analytic throughout a simply connected domain D, then for every closed contour lying in D, the closed contour integral is equal to 0. So again, this theorem here that we're going to prove is the converse of this Cauchy-Gorsatz's theorem for simply connected domains. This also means because both the forward and the opposite direction are both true, the forward direction and the converse are true. In other words, what that means is we can replace this with an if and only if. That basically equates every closed contour integral equals 0 with being f is analytic through a domain. So I've rewritten this here. So the closed contour C of f of z dz equals 0 for every closed contour lying in a simply connected domain D is true if and only if f is analytic throughout D. Now we're going to do a proof for this theorem. We are going to start with what we are given. F is continuous on a domain D, and we're also given that the closed contour over C f of z dz is equal to 0 for every closed contour C in D. The next thing I'm going to use in our proof comes from chapter 2, section 44, when we talked about antiderivative and Cauchy-Gorsatz's, which said that suppose we had a function f of z, it's continuous on a domain D, then any one of the following statements is true, then so are the others. And what we have, f of z has an antiderivative, as well as the integrals of f of z around closed contours lying entirely in D all have 0 value. So here we have that this last condition, the integrals of f of z around closed contours lying entirely D have all 0 value. And it's equivalent to saying that f of z has an antiderivative, capital F of z throughout D. So I'm going to write that here. To make more room for our proof, I'm going to get rid of the theorem I just used, but I'll put the result here that said f of z has an antiderivative, capital F of z throughout D. So what that means is f is the antiderivative of capital F. In other words, capital F prime of z is equal to little f of z. So that means that f then is analytic, because to be analytic, by definition, it means you have a derivative. So it's f is analytic in D, and that is exactly what we wanted to prove, that f is analytic throughout D. And I'm also going to say, according to our previous theorem here, that since f is analytic, then its derivatives of all orders are also analytic. So I just added that, but it's not part of our proof. Our next theorem is known as Cauchy's estimate, and also known as Cauchy's inequality. Suppose that a function f is analytic inside on a positively oriented circle, C of r, centered at z naught with radius r. That's the C of r here. And if m sub r denotes the maximum value of our modulus of our function on CR, then the modulus of the nth derivative at z naught is less than or equal to n factorial n sub r, r to the n. To prove this, we're going to use our extension of the Cauchy integral formula. We'll use this form right over here. So I copied it here. So the nth derivative at z naught is equal to n factorial 2 pi I over the closed curve integral f of z dz over z minus z naught n plus 1. I cleared out my Cauchy extension formula here to give me more room to finish this proof, which actually isn't very long. However, it does depend on another theorem from a section that I did not do a video on. And it's from chapter 4, section 43, which I skipped. And the theorem says, let C denote a contour of length L, and suppose that a function f of z is piecewise continuous on C if m is a non-negative constant such that m is greater than or equal to the modulus of f of z for all points z on C, which f of z is defined, then the modulus, or the absolute value, of the closed contour of f of z dz is less than or equal to m, which is the maximum for points z on C, times L, which is the length of the contour. I'm going to use this formula then to replace m times L to replace this part of my integral. First, I'm going to take the absolute value of both sides of this equation. So I have my absolute value nth derivative at z naught, and I should have put my absolute value sign here. Oops, kind of messy. I don't like it too messy. I'm going to factor out my n factorial 2 pi because that's always positive. Then I need to have my absolute value of, this should be 1 over I, but actually absolute value of I is the same thing. It's going to be 1. And then over here, this part of my closed curve integral will be the maximum value, mr, times the length. And since my radius of my circle is r, the length of the curve is going to be 2 pi r. And then I still have my 1 over z minus z naught n plus 1. I'm going to do a little bit of simplification. I can cancel out my 2 pi here with this 2 pi. I'm left with n factorial. Again, my absolute value, my modulus of I, or modulus of 1 over I, is just 1. And then I'm left with mr, and I have this r here, and I have z minus z naught n plus 1. But in this case, z minus z naught, any point z inside my contour minus z naught should be less than r. So this whole thing here will be less than r to the n plus 1. So again, I replaced the z minus z naught with r, but I also replaced it knowing that it'll be less than r to the n plus 1. So these cancel out, and I get n factorial m over rn. And this is exactly what I wanted to show, that the absolute value of the nth derivative at z naught is less than or equal to n factorial m over rn. And that is my Cauchy's estimate, and that it gives you an estimation for fn z naught, or it gives you kind of an upper bound. Also Cauchy's inequality, since it is an inequality. Now we're going to use Cauchy's estimate or Cauchy's inequality to prove the Liouville theorem. If a function is entire and bounded in the complex plane, then f is constant throughout the plane. Next, we will prove Liouville's theorem that says if a function is entire, in other words, it's analytic throughout the entire complex plane, and it's bounded, in other words, there's a maximum value for this function. It doesn't grow infinitely large anywhere. It's bounded in the complex plane. Then we can deduce that f is constant throughout the plane. We'll start with what is given. F is entire, and here I wrote the definition of entire, that a function is analytic at each point in the entire finite plane. So since it's entire, it's analytic inside and on any curve, closed curve C of radius r. Then from Cauchy's inequality that I have written here for your reference, then the absolute value of the nth derivative at z naught is less than or equal to m factorial m, which is the maximum value of the magnitude of f of z on our curve CR, divided by r to the n, r being the radius of our circle. If we let n equals 1, that means the first derivative evaluated at z naught, taking the magnitude, is less than or equal to, here n is equal to 1, so we have mr over r. And now, since f is bounded, there's a non-negative constant m such that the magnitude of our function is less than m. So we know that here we have some bound for our first derivative, and we also have a bound for our function. Since mr is our maximum on r, it's going to be less than m. So we're going to put that into our formula now. The magnitude of the first derivative evaluated at z naught is less than or equal to m over r. So at this point, we're talking about r, a circle, but we know that f is analytic on the entire complex plane. So we can take r to be arbitrarily large. So as r approaches infinity, what we see then is the bound for our first derivative is going to go towards 0. So in other words, this magnitude of the derivative evaluated at z naught is less than or equal to 0. Again, because we can take r arbitrarily large. And since m and r are both greater than 0, we know that m over r is not negative. So in other words, the derivative of f at z naught must be equal to 0. It's not going to be less than 0, in which case what we have is f is a constant function. And that's exactly what our Liouville theorem says. If a function is entire and bounded in the complex plane, then f is constant throughout the plane. I have moved Liouville's theorem up here for your reference, and we're going to use Liouville's theorem to prove the fundamental theorem of algebra, which says a polynomial p of z, which is equal to a naught plus a1z plus a2z squared plus anzn, has at least one zero. And this proof we are going to do by contradiction. So we start with assuming that p of z is not 0 for any value of z naught. We are going to then consider f of z, which is 1 over pz. We can see since pz is not 0 for any value, that f of z should be entire. In other words, it should still be analytic since we don't have any zeros in the denominator. So now we want to show that it is also bounded. To show that f is bounded, we're going to take our p of z here and divide by z to the n, and that'll give us w. So we're going to let w equal to a naught divided by z to the n, our a1 divided by z to the n minus 1, plus a2 divided by z to the n minus 2, up to an minus 1 divided by z. So that now we have p of z is equal to an plus w times zn. And a little bit of algebra that I have shown here will convince you that this last statement, p of z equals an plus w times zn, is true. I'm going to get rid of these algebra notes, but I am going to also write that this gives us that wn times z to the n is equal to pz minus an z to the n, this statement here. Now, just focusing on w here, by the triangle inequality, I can take the modulus of w, So I'm going to do this. I'm going to put the modulus sign here, the modulus sign over what W, this series that W is equal to. And by the triangle inequality, this is going to be less than or equal to the modulus of each of these terms taken separately. So in other words, the modulus of W is less than or equal to A naught Z over Z to the N, plus the modulus of A1 over Z to the N minus 1, all the way up to AN minus 1 over Z. As we plug in larger and larger values for Z, at some point each of these terms becomes bounded. And in fact, there will be some value R for when we're plugging in complex number Z greater than R, that this sum here, the modulus of W, is going to be less than modulus AN over 2. Remember, we can get arbitrarily large values of Zn plus 1, which makes this arbitrarily small. So there's going to be some point where this modulus W is less than modulus An over 2. Which means when I look at the modulus of Pn of Z, I have the modulus of An plus W times Zn, simply from this equation here, taking the modulus of everything, which is going to be greater than modulus of An over 2 times modulus of Zn, which is greater than modulus of An over 2 times R to the N, when modulus of Z is greater than R, which means then modulus of f of Z is equal to 1 over Pz, which is less than 2 over modulus of An Rn when Z is greater than R, which means that f now is bounded when Z is greater than R. And since f is continuous in Z less than or equal to R, and it's also bounded for Z greater than R, f is bounded in the entire plane. So I kind of minimize this so I can give myself more space, but we said that f is continuous and f is bounded in the entire plane. Now by Liouville, f of Z and P of Z are both constant, but P of Z is not constant because it's a polynomial, and we have reached a contradiction, which means P of Z must have had at least one zero. To review what we have covered in this video, we looked at consequences of the Cauchy formula extension. So we got these additional theorems, 1, 2, 3 theorems, and then from there we also got Liouville's theorem over here, which we used to prove the fundamental theorem of algebra. The three theorems that we got is, one, if a function f is analytic at a given point, then its derivatives of all orders are analytic there. The second theorem, let f be continuous on a domain if the closed curve integral of f of z dz equals 0 for every closed contour C and D, then f is analytic throughout D. The third theorem was Cauchy's estimate, also called Cauchy's inequality. Suppose that a function f is analytic inside and on a positively oriented circle C of R. This is radius R, centered at Z naught. If m sub r denotes the maximum value of the modulus of f of z on CR, then the modulus of the nth derivative evaluated at z naught is less than or equal to n factorial n sub r over r to the n. And finally, we had Liouville's theorem. If a function is entire and bounded in the complex plane, then f is constant throughout the plane. So that's it for this video. Thank you for watching.